Hello Math 110 students, welcome back. We're going to cover lesson 2.5 today. So some of our prep skills for this time are being able to locate numbers on a number line. And I'm sure many of you have seen this before in the past. We're just going to have a number line. This represents all of the numbers that we work with here, just integers, but certainly between those are the whole numbers, 2.5, 3.5, negatives and positives. Positive to the right, negative to the left of our number line. 0, we kind of write that in the middle, and then we go from there. If I wanted to locate the number negative 15 on the number line, the negatives are over here, increasingly small. Everything toward this is actually getting smaller. This is all getting bigger. So negative 15 is smaller than negative 10. Keep going to the smaller numbers and locate negative 15. So that happened to be right on one of these little tick marks here. What about if we've got something that's between those? So let's locate the following numbers. Let's locate, here's our number line I'm going to draw this time. We're only dealing with positive numbers, so I'm going to do the 0 for starting and then going for bigger numbers. 3, I would go over here. Now look, here's only 2 and 4. So I'm going to estimate about halfway through, but halfway between 2 and 4 to write my 3. 8.2, here's 6, 8, here's the even numbers are on this. So 8.2, 9 would be about halfway, and then further, closer to the 8 than to that middle point, I would locate 8.2. 13.4, I kind of go halfway between the 12 and the 14. There's 13. Halfway between those would be 13. Between 13 and 14 would be a halfway point. I'd back off a little bit more to the left, and I would just draw me a dot there. And then finally 19.9, I'm almost at 20, so I'm just going to back off a little bit and draw a little dot there. So those are my estimations. So we've done these many times. We've done bar graphs, pie charts, scatter plots, brought out percentage from those, from pie charts. We've looked at both frequency bar charts and then relative frequency, which is again the percentages. And then we also did scatter plots, and we're going to look at those a little more. So take a look at these, see if you can work on those for a few seconds. You're welcome to pause and then see if you can do those. Here's a pie chart. It shows the distribution of grades on a final exam. So the instructor says he just finished grading for a Calc 2 class with 31 students. And here is the distribution of grades. He had 16% A's, 32% of them were B, 7% C, 26% D, 19% F's. If I add all of these up, they should be 100%, or I'm missing something in there. Okay. So let's look at how we're going to do this. What percentage of students got a B on the final? 32%. Just reading it from the pie chart. How many students got a C on the final? This is a two-step question. We first need to locate the percentage. Here's our C, there's our 7%, but then we need to know the total. If he wants to know how many students got a C, we need to start with the percentage times the whole, give me the number of the part. So it was 31 students, 7%, so 0.07 times the 31 would give us the number of students. And then how many students got a D or better on the final? We'd have to do the 26 plus the 7 plus the 32 plus the 16, or 100 minus this, since this is just smaller, that would be 81%, 0.81 times the 31 students would be how many got a D or better. So the bar graph shows the number of students that got each of the first 5 questions on the final exam completely correct. Use it to answer each question. Which question was answered correctly by the most students? Looks like 25 students. So here's the number of students. Here's the question. So here the 25 students got question 4, and that certainly looks to be the most. How many people answered question 2 correctly? Let's see. 22.5 would be here, so I'm saying 23. What percentage of the 31 students taking the test got question 5 completely right? So I would say here would be about halfway. 12.5 would be halfway. We're not going to have students, so that I'm going to back off a little bit to 12. So I would say 12 out of the 31, that would be the percentage. Here, this is a scatter plot for us. Student scores on Calc 2 final. Here it shows the final grades for all 31 students. On the horizontal axis is the student's position alphabetically on the class roster. So 0 would be student 0, which here's, if you put it in alphabetical order, that would be 0, and then going all the way down. So student 0 out of 160 looks to be maybe 121. This would be the next one, so 0, 1, 2, 3. This would be person 4. So I guess maybe 0, this should be 1. Instead of starting at 0, we're talking about student number 1, 2, 3, 4. So I'm sorry, so 1 had to 121. 2 had made about a 79, 78. They're asking us next, how many students scored less than 80 points? So here's the 80. Less than 80 would be on the things that are not on the line. So 1, 2, 3 scored less than 80. 140 or more. Here's that. This one scored 140. 1, 2, 3, 4, 5, 6, 7, 8, 9 out of the 31. About what was the lowest score on the test? This is the lowest dot here. So it looks to be maybe a 42. So some other skills that you're seeing is that we're having to play a part in just getting estimation, estimating numbers, and reading. So here's just some general discussion things, just to get us thinking about mathematics a little bit. Write a brief description of 2 or 3 problems that you've had to solve outside of class. So here's just different personal responses. I know for me, I worked in engineering many years, so I used math extensively in electronics, doing electronics calculations. I do it in personal finance. What are my interest rates? What am I expecting to pay out of my payment if I've got this interest rate? So I'm constantly thinking of things in terms of math. I feel like I can get a value out of it instead of just something. What are some methods that you use to solve problems in your life? Do you think they apply to solving problems in college classes? So some methods may apply in both settings, or thinking about the issues that you're dealing with, considering possible solutions, choosing one and carrying it out, and reflecting on how well it worked. Sometimes you just have to go through an iterative process or an algorithmic process. I'm going to do this, 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 and then I'm going to get this. Is it close enough? I'm going to redo those things. So this gentleman called George Polya came up with a 4-step procedure for solving problems. You may find it useful as you go forward. Understand the problem. The best way to start any problem is to write down relevant information as you read it, especially with longer word problems. If you read the whole problem at once and don't do anything, it's easy to get panicked. Instead, read the problem slowly, carefully, write down information as it's provided. That way you always have at least here's the information to start with. Another essential step, carefully identify and write down what is it that they're asking you to find. What do you want me to do? And then look at the information that they provided. Sometimes there's just maybe extra information in there, and you have to determine what pieces of information are relevant to solve it, and then look for different formulas, methods, algorithms that you've learned. Step 2 is devise a plan to solve the problem. Good planning is the key to any successful operation. This is where problem solving is at least as much art as science. There are many, many ways to solve problems. A short list of common strategies and strategics includes making a list of possible outcomes. We saw this when we were doing some probability work. Drawing a diagram. Just do some trial and error. See if things can work. Finding a similar problem that you already know how to solve. And using arithmetic, algebra, geometry, or good old-fashioned common sense to kind of come up with a solution. Step 3 is carry out your plan to solve the problem. There's no point in making a plan if you don't actually and carefully execute it. If your original plan doesn't work, don't settle for failure and just give up. Just try a different strategy. There are many different ways to attack problems. Be persistent and never ever give up. Check your answer. In any problem-solving situation, you should think about whether or not your answer is reasonable. In many cases, you'll be able to use math to check your answer and see if it's exactly correct. But even if you can check an answer before you start, think about what your estimation should be. What would be something that would be expected? And if your math gives you that answer, that should be giving you a good guess that you've done the procedure correct. Here's frequently you look at stuff concerning number lines, and here is just a number line. This is a timeline that has important advances in medical sciences, and they just tell you to use this to answer questions 3 through 10. Which happened first? Timelines usually go from the left to the right, just like we read. Earlier dates to the left, and then the latter dates are to the right. Which happened first? The order. First heart transplant. Okay, which one? The first test tube baby or the first heart transplant? And here was the first test tube baby, and right before that was the first heart transplant. This was first, second from left to right. HIV was identified first in about 1985. Organs were grown from stem cells in about 2010. So here's from which happened first. Organs grown from stem cells, or the idea of identification of HIV. We would go through here. There's the HIV. Organs grown from stem cells. So this is first. That's the second. There are many ways that we can compare numbers once we're just kind of comparing one to the other. And there's both verbal description and basically symbolic in math, so that we can write this down. Here's our symbols. Okay? If I'm comparing two things and I'm saying that they are equal, I want to use that equal sign. 10 and 22 are equal. That's saying the left is equal to the right. They're the very same thing. Left side is the same as the right. X is approximately equal to 10. Here's a symbol we use for approximately equal to. It's like the squiggly version of this. This would be an estimation. So if I looked at maybe a scatter plot or something, and I said, what's the value of X? I go up, kind of do my estimation. This would be a good symbol to use to let everyone know it's not an exact value. It's just your estimation point. 10 is not equal to 15. This X not equal to 15. When I have something not equal to it, I do a little slash through the equal signs, and these say these two things are not the same. I can represent numbers from one side in comparison to another. These are just two numbers. 10 are less than 12, but I can also have something like X is less than 12. All the numbers X's that are less than 12. Here they also do it in a direction. If I've got a smaller number, that on the number line is to the left of the bigger number. All the numbers that are less than or equal to 10. So y is less than or equal to 10 can be written in this way. Y less than equal to 10. So all the values y's is either to the left or on the point 10 if I did my number line. 10 is greater than 6. 10, here's here's 10 to the right of 6. But also I can kind of look at these. This is the bigger side, the one that's open. The smaller size, this is my small one. So I would want this if I want to do to the left. I'm saying 10 is right of 6. But I also like to write this in terms of from left to right, 6 less than 10. That way you've got that version of it that you know, here's the numbers to the left, then to the right. N is greater than or equal to 10, so here's all the numbers n that are bigger, this is the big side, that are bigger than 10, but it can also be equal to 10. So these are two conditions, the bigger numbers and then or equal to. Yeah, here is just some writing those number lines. 1965 occurred before 1975. It was to the left. 2010 is greater than the 1985, so it's to the right of the 1985 if we did a timeline. So the two most recent events on the timeline are organs growing from stem cells and skin cells growing into stem cells. So here's those two last numbers. How do the dates compare? They look almost the same, but certainly if I write this one first and this one here, skin cells came second. I would do this and then this one. I wouldn't want to switch these things. Okay. Use one of the symbols introduced in the previous paragraph to describe the relationship between the dates for organs being grown from stem cells and stem cells being grown from skin cells. So the organs are less than the skin cells. Okay, but we all could, so this also could be the same time because here they're pointing to here, so they're going to say less than or equal to the year organs were grown were less than or equal to, because we can't really discern if they're any different. So how about estimating using bar graphs? We've done this in class. Estimate the monthly cost of homeowners insurance in California. So here's the cost per month. We want monthly cost. We want it in California. So here are different states. And if we want California, we have to identify the California one. Then we go up. There's 80, 100. Halfway through them would be 90. Halfway through that would be 90, 85. So I'm thinking that's maybe like 82. So they're saying about 80, too low because the bar ends just a tiny bit above 80. So using your answers to question 11 and 12, we're thinking it's bigger than 80. 82 is what I would have guessed. But the cost, here they put a lower bound on it. There was certainly bigger than 80. So they just said, if I'm going to do that, I could write it's bigger than or equal to 80. And I'm thinking we could just say that was bigger than 80 for California, because it certainly wasn't on the line for 80. Suppose that you were planning a move to Arizona and wanted to budget a monthly amount for homeowners insurance. Would you prefer an overestimate or an underestimate? Anytime you're budgeting for items and you don't want to get too close to your budget and you either go over, you don't have enough money, you're going to be late on the payments, I always want to overestimate for a budget so I don't risk not having enough money. It's better to overestimate and then have some extra money left over than getting too close. So here's what estimate would you use for the monthly cost of homeowner insurance in Arizona? So here, if you were going to budget for this, that would be, I'm going to budget a little more. So let's just say $60. It could be $59, $59.50. Let's not risk that estimation, and I'll just call it $60. And then that would give me a little buffer if it happened to be that much. So here's our scatter plot once again. Here is where we always said before that we were going to use base year as 0, 1975 is our base year. That would be 0, and then we would count from there. So this would be like 5, 10, 15, 20 years from 1975. But here they just went ahead and put the year down at the bottom. And they wanted to estimate something, estimate the minimum wage. Here's the minimum wage in 2009. Basically, you're just going to go over to what you think 2009 is. I would go the furthest one, the furthest closer to 2010. And then go over here. There it is. I'm going to say the minimum wage is, let's say, $7.25. Do you think your estimate may be too high or too low? It could be too low because the actual one has height more than 1/4 of the way between 7 and 8. And suppose that a high school graduate of 2009 was trying to figure out the budget for college while working a minimum wage job. Would she have preferred an underestimate of the minimum wage or overestimate? We'll do the opposite here. We're going to do an underestimate. So in this case, I would kind of back down a little bit and I'd go from there. So that way I've overestimated my cost, I've underestimated my revenue coming in, and that would give me some buffer if either one of them were off. Okay. So an underestimate says she doesn't plan on living on more money than she really gets. Okay. Here's some common verbal descriptions that you may run into. Refer back to this, and this is basically saying if I hear less than, I'm going to use this then. The number is less than 6. In less than 6. Fewer than. For this, the greater than symbol, greater than, more than. This is the less than or equal to at the most. So at most, the biggest it can be is a certain number. All the numbers at most 10. Any number at the most 10. That would be all the 1, 2, 3, 4, 5, 6, 7, 8, 9, but up to the 10 and including at the most. No more than 10, that's another very same thing. A maximum of 10 or less or lower than 10. Less than or lower than 10. That needs to be included as well. So 10 or less, 10 or lower is what they're trying to get at here. The greater than or equal to, at the least, the very least, the smallest, all the numbers that are bigger than that number, at least 10, that would be all the numbers in that are bigger than 10, at the least 10, so 10, 11, 12, 13. No less than 10, a minimum of 10, 10 or more, 10 or higher, because we need that number in there to be equal to that as well. So here's a couple of different things, and we're going to make a statement and see how this works in there. We can fit at most 12 people on the slow ride pedal bus. So that includes 0, 1, 2, 3, 4, 5, at the most 12. So let n be the number of people, and then n is all those numbers that are smaller than or equal to 12. The biggest it can be at the most is the 12. So 10 will work. 10 is smaller than or equal to 12. It's estimated that there are at least 50 ways to leave your lover. At the very least, 50. Could be 51, 52. So n can be bigger, or L, if L is the number. L can be bigger than or equal to 50. 51, 52, 53. I get a text alert from my bank if the balance of my checking account drops below 100. So it has to be less than 100, below 100. So B is the balance. B is less than, smaller than 100. If all of a sudden my balance dropped down to 75, there's that text alert coming in. Any amendment to the U.S. Constitution will only be enacted if more than 37 states vote to accept it. So let S be the number of states that vote to accept it, and will only be enacted if S is more than 37. It can't be 37, it has to be bigger. So S greater than 37. 40 would work, 38 would work, 37 would not work. We don't have that equal sign there. Okay. So those are some more concepts that we're going to be working on in this unit. Hope you enjoyed it. See you next time. Have a good day.